Okay, thank you.
Good morning, everybody. First of all, many thanks for coming, and I really appreciate Professor Vargas to provide me an opportunity to present my work for the flow assurance team in Rice University. My name is Khosrow Jarahian, PhD student in the flow assurance and scale team in Heriot-Watt University. And it's my great pleasure to present my work entitled Mechanistic Study of Scale Inhibitor Retention in Carbonate Reservoirs for Precipitation Squeeze Treatment. Today I'll go through definition of scale, mechanism of scale formations, mechanism of scale inhibitor retention, experimental section, which includes experimental results, modeling, the system which is ongoing, at the end, summary and conclusion. As almost of you probably familiar with the scales, scales is a crystalline precipitation resulting from the precipitation of mineral compounds in water. So in our case, we are focusing on water chemistry, what the mineral compounds in water, but in your case, you are focusing on the compounds like asphaltene, resin in the crude oil. This is the only just difference between our works, but at the end of the day, the all systems called scale. And oil field scales typically consist of any inorganic scales like calcium carbonate, barium sulfate, strontium sulfate, along with other debris like asphaltene, wax, corrosion products, and sand. There are three common different types of scales: carbonate, sulfate, and halide scales. Carbonate and sulfate scales are induced by different changes in conditions. For instance, in carbonate scales, as you see, the carbonate scale formation happens because of temperature increase or pressure decrease. And this alteration in condition allow the release of the carbon dioxide from the system and increase the pH. And the system at the moment is prone to get precipitate of calcium carbonate. So if you look at the reaction, higher pH means higher risk of calcium carbonate formation, and lower pH, which means that CO2 is in the system, and the reaction according to the Le Chatelier principle goes from the right side to left side, which means that the calcium carbonate is consumed and there is no risk of carbonate formations. For sulfate scales, these type of scales are formed because of mixing of incompatible waters like formation water and seawater. And the seawater is injected into the oil reservoirs to maintain the well pressure. So once the seawater is injected into the oil reservoirs, it's enriched with anions like sulfate, and the formation water, on the other hand, is enriched with divalent cations, particularly barite, barium, and strontium. Now, when they are the seawater is injected into the oil reservoirs, and these two waters combine together, mix together, and the system will be incompatible, and barium sulfide and strontium sulfide will be formed. And the third type of scale, which is recently more important for production engineers, is halide, and it's formed because of changes in concentration of particularly sodium chloride around the wellbore because of evaporation and dehydration. Now, how to remedy, how to solve the problem of scale formation. One of the most important procedures to solve the problem to avoid the formation of scales is squeeze treatment. The chemical scale inhibitor injection, which comprises of 5 stages: pre-flush, main treatment, oil flush, shut-in, and back production. In pre-flush, the mutual solvent, which mainly consists of surfactant solution, is injected into the oil reservoirs through production well to prepare the surface of rock for retention of scale inhibitors. And the second stage, main treatment, the scale inhibitor is injected into the oil reservoirs, into the wellbore. And at this stage, the expectation for scale inhibitor is to be retained as much as they can. And in oil flush, we push scale inhibitor already injected by seawater or brine. The system will be shut in for 48 hours or 72 hours. And this period of time, the well will be put in a back production. And in back production, the scale inhibitor should be redissolved or desorbed from the rock, the surface of reservoir rock, to go in water stream coming from the reservoirs to prevent the reaction between anions and cations and formation of inorganic scale. So in squeeze treatment, we have 3 parameters which can be taken into account. First, the scale inhibitor retention should be maximized by precipitation squeeze treatment, and the cost of squeeze treatment which be minimized, because as you know, it's a chemical, scale inhibitors are chemical, and they should be minimized in terms of cost. And the period of oil production deferment, that's very important. It should be, again, minimized, because it's the favorite, it's the desire for the oil companies. So squeeze treatment should be optimized by consideration of 3 parameters: period of oil production deferment, scale inhibitor retention, and the cost of chemical scale inhibitor injection. So there are two different mechanisms for scale inhibitor retention: adsorption and precipitation. As you see in adsorption, some scale inhibitors will be adsorbed on the reservoir rock through electrostatic interaction between the scale inhibitor with the reservoir rock, with the mineral formation, and it will be described by the adsorption isotherm, which is a function of the concentration of scale inhibitor, pH, and temperature of reservoir. However, in precipitation, the scale inhibitor should be able to interact with divalent cations, either from the solution or from the rock, to form the precipitate. And this mechanism should be happen at the same time in the oil reservoir to have long life space treatment. Now the big question is how to distinguish between adsorption and precipitation. If you plot apparent adsorption versus final scale inhibitor concentration, as you see in the figure, once for 2 different mass volume ratio, the apparent adsorption doesn't change too much, just moving along the adsorption isotherm. It means that the pure adsorption is occurring. However, once for different mass volume ratio, the apparent adsorption starts to diverge from the adsorption isotherm, it means that the retention mechanism is changing from pure adsorption to coupled adsorption and precipitation. Now let me talk a little bit about the scale inhibitor. Scale inhibitors are polyvic acids, so they will be dissociated and generate negative species depending on the pH of solution. Higher pH of solution higher, more dissociated scale inhibitors. So we can conclude that for getting high retention of scale inhibitor in the oil reservoirs, we should consider higher pH, because the scale inhibitor is dissociated form and it can interact with the equivalent cations, particularly calcium.
Specific of carbonate formations, or it's the same thing for sandstone?
It's just a specific, the scale inhibitor you are talking, or the
This mechanism for retention.
For retention, it's for any type of reservoirs, but for carbonate, I'll explain to you later, because of high reactivity, high chemical reactivity of the formation rock, precipitation is more dominant than pure adsorption. But in sandstone, if you inject seawater, for instance, as the concentration of calcium is low, the scale inhibitor cannot be dissociated, can't interact with, for instance, calcium and form precipitate. And pure adsorption should be the predominant mechanism. But to have higher retention of scale inhibitors, we should consider precipitation plus adsorption. Okay? Now, the scale inhibitor has been dissociated already. As I said before, it depends on the pH of solution. Now, it can combine with calcium, particularly, because it has more affinity to be involved in chemical reaction with scale inhibitor to form the complex. This complex is precipitate, is called precipitate. So, for retention, for complexation process, we need two things: higher pH. pH controls the dissociation of scale inhibitor, and higher concentration of calcium. Just bear in your mind. Now I'm going through the experimental method. So it's very simple. The experimental methodology is very simple. It's static adsorption, static compatibility. But why we consider compatibility test? It's very important for scale inhibitor injected into production well through squeeze treatment to maintain, to remain stable, to remain compatible with the solution in which it's prepared till the reach of the reservoir rock. Otherwise, they don't work effectively. So, first, the scale inhibitor should be prepared in different concentrations and adjusted at a specific pH, in our case pH 2, 4, and 6, and put in the oven and for 24 hours. On the other hand, we have crushed calcite and dolomite in our case because we are working on the carbonate rocks, and put a specific amount, around 40 milliliter of scale inhibitor with different concentration, to the plastic bottles, put in the oven for 24 hours simultaneously with compatibility test. And after 24 hours, the plastic bottles will be removed and filtered. So the solid will be collected from on the filter paper, and the supernatant, which is filtered actually, will be analyzed by ICP, inductive coupled plasma. It's very, very accurate analytical method, and we can use this formula to calculate the amount of apparent adsorption, where V is volume of solution, and this is the terms in parentheses is a difference between initial and final scale inhibitor concentration, and M is mass of the substrate. As you can see in this formula, less amount of substrate, higher amount of apparent adsorption. We have used two different scale inhibitors which are widely used in the oil industry, DET, PMP, and PPCA. DET, PMP is a representative of phosphonate scale inhibitors, and PPCA is a polymeric one, but tagged with phosphorus just to detect by ICP easily. Now, as you see in the figure, I'm talking about the ETPMP dolomite sample, the system. From 0 to 100 ppm, there is no changes between the apparent adsorption result, which means that from 0 to 100, the mechanism for retention of scale inhibitor is pure adsorption, but above 100 ppm, the system starts to diverge, which means that the coupled adsorption and precipitation is occurring. So we can conclude that although both mechanisms, pure adsorption and precipitation, are occurring together, precipitation is more dominant mechanism for the retention of scale inhibitors. And secondly, as pH increases, the amount of apparent adsorption increases. I already told you dissociation of scale inhibitor is strongly dependent on the pH of solution. So higher pH means more scale inhibitor dissociated, and as a result, more apparent adsorption. And for pH 2 and pH 2 and 4, the results are quite similar, and it may be attributed to the amount of apparent dissociated scale inhibitor. But for pH 6, if you look at, the system starts to diverge from pH 2 and 4, and I let you know what the reason behind it. Now we change the substrate from dolomite to calcite. Just a thing, let me go back to the dolomite. Just bear in your mind that for 5 gram pH 6, the amount of apparent adsorption is 25 milligram of scale inhibitor per gram of substrate. But for calcite, it's lower. It's maybe around 12 milligram per gram. And like DETPMP in dolomite, as pH increases, the amount of apparent adsorption increases. So it's very interesting. The point is that we expected to get more apparent adsorption on calcite than dolomite, but it wasn't in reality. So basically, dolomite is less reactive chemically than calcite, and we would expect to get less precipitate. But as I showed you, it wasn't. And I tell you that it's because of the final pH of solution in DETPMP dolomite. The final pH in DETPMP dolomite is higher than calcite DETPMP, which can contribute to scale inhibitor becomes more dissociated and more apparent adsorption. Did you get the point, guys? Okay. Now for PPCA with dolomite, the story is completely different than DETPMP. For PPCA, as pH decreases, the amount of apparent adsorption increases. And it might be attributed to the calcium concentration. For PPCA, the final pH that I'll show you later is around 8. The system will be buffered because of carbonate in the system, and the carboxylic acid in PPCA will be buffered around 8. So it's pretty enough dissociated. So now PPCA needs more calcium to get precipitate. At pH 2, pH 2 is more acidic, so it can dissolve more dolomite or calcite in PPCA and generate more calcium and magnesium in situ. So more calcium concentration, more calcium accessibility, more apparent adsorption. For DETPMP, just bear in your mind, first, I'm talking about the differences between DETPMP with PPCA. As pH increases, apparent adsorption increases. But for PPCA, as pH decreases, apparent adsorption increases. And another difference is calcite. We got more apparent adsorption of PPCA and calcite than dolomite. And it might be attributed to the calcium in calcite. Generally speaking, calcium concentration, calcium is partially higher in calcite than dolomite. Dolomite is a combination of calcium and magnesium, but calcite is purely calcium carbonate. So calcium is higher in calcite. So the calcium which PPCA needs to get precipitate in calcite system is higher, and as a result, apparent absorption increases. So now I'm talking about the pH. pH is another indication of solution properties to confirm the corresponding apparent absorption results. This is the ETPMP carbonates at pH 2 and 4. So for compatibility test, as you see in the figure, no mineral present. Just 8 inhibitors put in the oven for 24 hours at reservoir light temperature, 95 centigrade degree. There is no changes in final pH between initial adjusted pH with the final pH of compatibility test. So DETPMP is completely compatible with seawater. But once the substrates, dolomite or calcite, doesn't matter, are added to the system, the pH, the final pH starts to go up to around 7 and 8 for calcite and dolomite respectively. And once the retention mechanism changes to couple absorption and precipitation, if you look at the curves for both of them, the final pH starts to go down because of missing calcium and phosphorus from the system. Moreover, the final pH for dolomite is higher than calcite. And that's the point why DETPMP is retained more on dolomite than calcite. So the higher pH, more dissociated scale inhibitor, and more apparent absorption. For pH 6, the story is different because now the ETPMP is not compatible, which is not our favorite actually. So if you look at the final pH, it goes down because of reaction between calcium from seawater with the ETPMP, but like pH 2 and 4 that I already showed you, the dolomite, the final pH of dolomite, the ETPMP system is higher than calcite, and we got more precipitate for the ETPMP in dolomite than calcite. Now for PPCA, the final pH, so in compatibility test, again, PPCA is completely compatible with seawater, but for pH 2 and for pH 4, if you look at the figures, so the final pH will be buffered around 8. So PPCA now has been enough dissociated in the system. Now it needs calcium. It needs calcium to bind with PPCA to get precipitate. Now the question is, in which pH we can get more calcite? The question is clear, it's obvious. At lowest pH, the calcium and magnesium, particularly in dolomite case, will be more generated compared with, for instance, pH 6. At pH 6, rock dissolution is negligible. But for pH 2, the rock dissolution is more than pH 4, more than pH 6. So we got more calcium, more magnesium at pH 2, and accordingly, apparent absorption for PPCA increases as pH decreases. That's actually the reason why PPCA behaves different than DETPMP. For pH 6, there is a difference between PPCA and DETPMP at pH 6. DETPMP was incompatible, but PPCA at 3 different pH values completely compatible, no reaction without any minerals in the system. But if you look at the system for pH 6, the final pH will be around 8, and rock dissolution is negligible. So the system has been dissociated, that's true, but the calcium which is in the solution is not enough to get precipitate at pH 6. So the apparent adsorption decreases once pH increases. Now I'm talking about the calcium, normalized calcium for DET-PNP. So for pH 2 and pH 4. If you look at the calcium actually maybe except these points maybe because of analytical error reaches to a plateau like here 1 point times and 1.2 times for pH 2 and 4 respectively in calcite, but for dolomite it goes up for instance at pH 2, but because of involvement in chemical reaction with DET-PNP it goes down and levels of around 1, which means that the whole of calcium in the system generated by rock dissolution will be consumed, will be used by DET-PNP, and there is no excess of calcium in the solution. But for pH 4, so the system DET-PNP in dolomite, as I said before, the final pH is higher, right? So it's already dissociated, completely dissociated, but it needs calcium. So compared with pH 2, the rock dissolution is less, right? So the calcium in the solution is less than at pH 2. So DET-PNP in that case needs to make up to take constant calcium from another source. So another source for a calcium compensation is seawater. Although it's low, around 428 ppm, but it can use and get precipitate. If we had more calcium in the solution, we would get more precipitate. For pH 6, at the DET-PNP, again, in compatibility test, calcium goes down because of, again, complexation between DET-PNP with calcium from seawater. And the difference between the calcium generated in situ, the normalized calcium between calcite and dolomite is negligible. They behave quite similar because pH 6 is not as acidic as pH 2 or pH 4. So for PPCA, as I said before, pH 2 generates more calcium, more apparent adsorption. And for dolomite, the systems reaches a plateau, which means that the whole of calcium will be consumed in complexation and no access in the solution. But for calcite, we have the access of calcium, and the calcium goes up continuously. For instance, 3 times at pH 2 and 1.8 or around 2 times at pH 4. For pH 6, at highest concentration, which is 4,000 ppm, in the system, so at pH 6, rock dissolution is negligible. So, but he can use the calcium from the solution at highest concentration. That's why it goes down from the baseline of normalized calcium. Now I'm talking about the surface chemistry, just to look at the morphology, the surface of calcite and dolomite grains before and after scale treatment. So if you look at the calcite and dolomite, pH 2, and I just have chosen the highest concentration because it's more important. We have got more precipitate and we could detect significant amount of the phosphorus. And the phosphorus detected by EDX from bulk precipitate in dolomite is higher than calcite, which can confirm the corresponding apparent adsorption result for DET-PNP. And we could detect some phosphorus around actually the calcite and dolomite, which might be because of the adsorbed and adhered scale inhibitor complex on the surface of grains. For pH 4, the amount of phosphorus around the calcite grains for calcite is negligible. It's not too much, but for dolomite it's negligible. If you look at it, you can see some precipitate actually around the dolomite case. But for bulk precipitation, the phosphorus detected are quite similar, no differences, big differences between them. But for pH 6, the phosphorus is higher than pH 2 and pH 6. Again, it confirms the apparent absorptions. So ESCM EDX results for DET-PMP is completely consistent with the apparent absorption results, with pH results and calcium results. And for compatibility test, no mineral in the system, as you see, we can detect precipitate. Actually, we could observe precipitate visually and detect some phosphorus, which is similar to the phosphorus detected in dolomite and calcite. They're very close, very near actually. Now for PPCA carbonates, because of low content of phosphorus in PPCA, we couldn't detect any phosphorus, right? So we need to change, although we observed visually precipitate on the filter paper, as you can see on the right side. So we need to change the analytical method to particle size measurements. So for once we use the biggest lens, 300 millimeter lens, as you can see, there is a good consistency of the results. We use the biggest lens just to detect the big, large particles, particles in the solution. But once we change into the smallest lens, 45 millimeter lens, for pure adsorption, as you can see, we couldn't detect any peak. But once the apparent adsorption mechanism changes to coupled adsorption and precipitation, we could detect a peaks, which means that some fine particles are existing in the solution. Now, that was actually the story of experimental results. Now I'm going to the modeling part of our experiment. This model, we are at the moment trying to develop the geochemical models to characterize the system, to know what's going on the system. So in that system, as I said, we are working on carbonate. So we need carbonate equilibrium equations first, scale inhibitor dissociation equation, and calcium magnesium binding equations. We need to combine all equations together and solve it to predict what's going on, to predict why, for instance, DET-PMP has been retained more on dolomite than calcite. Now, this one actually I already explained, more higher pH, more dissociation. And this is actually like summary of the equation. So this is the simple example of the carbonates. So this is the calcium carbonate. In calcium carbonate, we have CO2 in an aqueous phase. Now it can be react with H2O with water in bicarbonate equations and generate bicarbonate plus proton. So this is the equilibrium reaction. We need equilibrium constant, which is defined by Y2 times Z divided Y1. And this species, this bicarbonate, is not stable. It will be dissociated to carbonate plus H proton, and it has another equilibrium constant. On the other hand, calcium plus carbonate, which can generate calcium carbonate, and this system will be described by solubility product, and water as a polypolypolyvic acid will be dissociated to proton and hydroxyl. So now in this system we have 7 unknowns and 4 knowns. We need 3 more equations to be able to solve the problem, to solve the equation, sorry. Now, the 3 equations, 2 mass balances for carbon and for calcium, and 1 charge balance for equation, for equation. So, the carbon comes from, first, carbon dioxide, Y1, plus Y2, plus Y3, and plus Y4, right? Y1, Y2, Y3, and Y4. And calcium comes from the calcium ion and calcium carbonate, which is M1 plus Y4. This is 2 mass balance equations. And 1 charge balance, so, sorry, we have to consider all cations and anions. So minus Y2, because this is the negative actually ions, so anions, minus 2 plus Z, minus 2Y3 because it has 2 valence, and 2M1, and minus W. This is the charge balance of the system. Now we have 7 unknowns and 7 knowns. Now we can solve the problem. If we combine the system, the final equation will be this. This is Y4. Y4 is calcium carbonate concentration, which is a function of M1, concentration of calcium, and Z, which is concentration of proton or pH of solution, equals the total carbon minus this equation, which is not dependent actually, which contains solubility products and equilibrium equations. This is the carbonate equilibrium. Now we have to consider scale inhibitor dissociation equation. So this is the dissociation scale inhibitor, as I already told you. Depending on the pH of solution, they will be dissociated. Okay, right? So for the first stage of dissociation, it can generate H plus with this species. And for that reaction, for that equilibrium reaction, we need equilibrium equation X2 times Z divided X1. And it goes on like that. So for Kn, if you look at the pattern, so for K2, X3, Z, X2. For Kn, Xn plus 1 times Z divided Xn. And on the other hand, we need to mass balance for the total scale inhibitor, which comes from X1, X2, X3 till X plus N1. Now we need to rewrite the equations in terms of as a function of X1, right? This is the mass balance, and if we put all results together, if we put X2, X3, X4, because they are not independent equation, they are dependent equations, so you can rewrite as a function of X1, X1 times G1Z. This is the new function, just to make sure it's not for instance, the function that we described already for carbonate system, x1 times g1z. And g1z is a function of the pH, or concentration of proton. So we have done normal carbonate equations, scale inhibitor dissociation, and calcium. Now we are going to calcium magnesium binding, right? So the calcium will be react with the dissociated, just first stage of dissociation scale inhibitors in terms of that. And like dissociation squeezed equations, we can find a pattern for the constant of calcium magnesium binding, right? At the end, we reach this equation. Now we have three functions, three equations. We have to combine these results together and solve by Newton-Raphson to find Z, which is very important, pH of solution, M1 as a concentration of calcium, and M4 as a function of magnesium, particularly in dolomite case. In calcite, we don't have. This equation, these functions will be just as a function of Z and M1. The function will be changed actually for calcite. But for calcite and dolomite, as we have calcium and magnesium, the F1, F2, and F3 will be dependent on the concentration of calcium and magnesium. Now, as a summary and conclusion, both pure adsorption and coupled adsorption precipitation happens, but precipitation is more dominant mechanism for the scale inhibitor retention in carbonate rocks. As phosphorus content increases, the reactivity of scale inhibitor with the rock, with calcium, magnesium increases, and we get more precipitate. In PPCA carbonate system, as pH decreases, apparent adsorption increases, and it might be attributed to the calcium concentration which PPCA needs to get precipitate. At lower pH, we get more calcium and more apparent adsorption. And PPCA retains more on calcite than dolomite. DET-PMP, as pH increases, the apparent adsorption increases. And it reminds us that two different things happens in the system for DET-PMP PPCA. In DET-PMP, pH controls the retentions, but for PPCA, calcium accessibility, calcium concentration controls the system. And DET-PMP retains more on dolomite than calcite, because the final pH of dolomite is higher than calcite, and DET-PMP, which causes DET-PMP more dissociated, and as a result more apparent adsorption. So for particle size analysis, which was used for just PPCA because we couldn't detect any phosphorus by EDX, the results clearly show that if we use the smallest lens, we could detect some fine particles in the solution which can confirm the corresponding apparent adsorption results. And for EDX, we could detect phosphorus on bulk precipitation and a little bit phosphorus on the calcite and dolomite grains, which means that the precipitation happens in the bulk, not on the surface of the rock, just in the bulk of solutions. At the end, thank you very much for your attention, and it's very actually open to ask your question, and I would be grateful if you tell me your comments. Thank you very much.
Thank you.
Hopefully you enjoyed it. And this is our sponsors. At the moment we have 12 actually sponsors, but for previous phase of our project, because we have different types of different phases, we had 22 before oil price crash.
Sure.
We had 22 sponsors, but at the moment we have 12 sponsors. The number of sponsors
was very good.
decreased already. Yes. Okay. Thank you very much
Okay.
for attention. And
Thank you. Any questions from the audience?
hopefully you enjoy it.
It's interesting.
Thanks.
You have one question?
No, you go first.
No, you go
You're the
first.
advisor.
Any questions?